It's sp3 hybridized. So we're going to have 3 CH3s coming down like legs of a tripod and the lone pair up on top. It's going to be tetrahedral, which is what sp3s look like. So there is going to be a slight dipole towards the nitrogen. Nitrogen is more electronegative than carbon, and it's going to pull a little bit of that electron density in for itself. So it's slightly polar, but not quite as much as that CH3OH. Go ahead and erase that. So if we know that CH3OH is the most polar, is it going to do the most or the least to stabilize that positive charge? It's going to do the most. Yeah, that polar solvent is going to stabilize that positive charge. Because it is significantly, so it's a partial negative charge there. But that's got the greatest partial negative charge out of all of these. And that right there is what's going to stabilize that positive charge. So it's going to go ahead and dissolve in there. That's going to be our number 3. What about our last one, or number 3, our third one? How is that going to do with stabilizing that positive charge? Terribly. Yeah, it can't do anything for it at all. So it's just not going to dissolve in it at all. There's going to be no association, or hardly any at all. So that'll be our 1. Process of elimination, put that at 2. Any questions about that?
Could you tell that just by looking at the lone pairs of electrons on the nitrogen and the oxygen? Because there's 2 lone pairs on the oxygen and the
Yeah, I'm not actually 100% sure. Her question was, could you tell that by looking at the lone pairs on the nitrogen and the oxygen? And that brings up a really good point. There is 1 lone pair on the nitrogen and 2 on the oxygen. I would say it has more to do with polarity because oxygen is used to having 2 lone pairs. So it's not going to be negatively charged carrying 2 lone pairs. Nitrogen is going to be negative or positively charged carrying 1 lone pair. That's a good thought though. I'm not 100% sure. That would be a great question for Dr. Bean or Dr. Leon, whoever you take. But yeah. Any other questions about that? Raise your hands high, get some help, now's the time, for sure. Alright, so number 5. Draw all structural isomers resulting from the monobromination of the compound shown below. Monobromination, what does that mean we're going to do to this molecule? Yeah, we're going to put 1 bromine in there. We're going to put a Br on this molecule in place of a hydrogen. But look what this last thing says. You will be penalized for duplicate and incorrect structures. The quickest way to tackle a problem like this is to look at how many distinct types of carbon we have, and if there are any identicals. Let's just pick a random one. Let's start on the left. We'll call that carbon A. Are there any carbons on this molecule that look exactly like A and behave exactly like A?
The last one.
The 2 methyl groups adjacent to it are completely identical. This bond right here between this carbon and this carbon is freely rotating. So all 3 of those methyl groups that I marked A are going to be spinning. They're all connected to exactly the same thing, and they're all exactly the same group, and they'll all occupy every position in that spinning. So all 3 of those are identical. So we're going to label all 3 of those A. How about the next carbon in this one I marked right here? Is that unique?
Yes.
Let's call that one B. Next one, we'll call it C. Down below, we'll call it D. Is this one different?
Mm-hmm.
Yes, we're going to call it E. How about here? Is this one different?
No.
Yes. Yes, it is different. So it might look a little bit like C, but if you look at what C is connected to, it has an extra methyl group on there. So we're going to call this F. Moving down the line, are these similar to any we've seen before?
Yes.
They are similar. Are they exactly identical? Perfectly? No, they're not. If this molecule were perfectly, completely symmetrical, then yes, they would be the same. In other words, if we removed that methyl group right there. Then our answer would start to change. We would then label this C, we would label this B, and we would label these A, because it's completely symmetrical. However, it's not completely symmetrical. So you have to account for that. So those are actually distinct carbons. Call that F, G, H. Do we call this I? No, H, H, and H. All three of those are completely identical. H and H. So we've marked all these different types of carbons. Are there any of them that we marked that we can't put a bromine on? Yeah, B and G. Why can't we put a bromine there?
They're satisfied.
There's no bond to hydrogen. Yeah, first thing that has to happen, it's going to rip off a hydrogen. One of the bromine radicals is going to come in and rip off a hydrogen. If there's no hydrogen there, there won't be any reaction there. Carbon can't have a fifth bond. So we can actually go ahead and cross out B and G, because we don't need to worry about those. Now, all we have to do, we have to count the number of distinct letters that we have. So we have an A, that's 1, C, D, E, F, H. So that's 6. So now what you're going to have to do is redraw this structure so that you have a total of 6. And this might take a hot second. So that's 1. We're going to draw 6 of them. And 6. And what we're going to do, we're going to add a bromine to every single distinct type of carbon. So we're going to add 1 right here. That'll be our A. So then, do we need to add a bromine to this carbon or this carbon on any of our structures? No, because it would basically be adding it to the exact same carbon. And you see in the directions, you will be penalized for duplicate and incorrect structures. So that's a really good way of knowing whether you're going to accidentally make a duplicate structure. So don't put 2 bromines on A when you're doing these. So let's find our next letter. We crossed out B, so let's go to C. C is that guy. So we're going to put a bromine on C. Br. Likewise on D, we're going to put 1 there. E, put right there. F, we can put right here. Can we put 1 on G? No, we crossed it out because there was no hydrogen there. And we can put 1 on H. And that's it. If you have any questions about that, raise your hand. And we'll come around. How y'all feeling? Good? Bad? Shake it out. Take a deep breath. It's going to be fine. I have a feeling y'all are going to do really well. First test isn't too bad. And it seems like y'all are picking this up pretty well. So, that's good. Alright, let's go ahead and move on. Number 6. Rank the following anions in order of increasing basicity. That's a tricky question. Oh, do you want to see this one still? Sorry about that. Yeah, I'll leave that one up for a little bit. Okay. Rank the following anions in order of increasing basicity. Very first thing I would be thinking about, what do bases do? What is a base's job?
Proton
Accepts a proton. It's going to grab a proton. There are multiple different definitions for acids and bases, and we're going to use the proton transfer definition. So what this is going to do, it's going to grab a proton. What on all of these molecules would grab a proton? This lone pair, this negatively charged lone pair. If it's charged, is it stable? Not as much, no. And so it's going to want to grab that proton in order to satisfy that negative charge, to make that negative charge go away. But not all of these are equally stable. So we're going to look at all three of these. Let's direct our attention to the third one. What's missing on the third one?
Double bonds.
There's no double bonds. There are no double bonds. There's one here, and one here, one here. There's not one there. And there's none on the third. What can those double bonds do with that lone pair?
Resonance, right?
Resonance, yes. What that's going to do, the big benefit of resonance, is that it's going to delocalize that negative charge, which is going to make it more or less stable.
More stable.
More stable. Yeah, many hands make light work, so if more atoms are sharing the load of that negative charge, it's going to be more stable. It'll be more okay with that. So looking at the first one, let's draw some resonance structures here. One of the things that can happen, this lone pair can pop over here and kick this double bond out onto the end. So we would see a lone pair and a negative charge there. We formed a new double bond, remember, about that bond right there. And that's what that first arrow, that arrow, is. And then we have our first double bond that didn't get touched. It can go the other way. Let me actually put this one in red. It can go the other direction. So it can pop over onto that bond and kick this bond out onto the end as well. Are those two structures identical? They are. But all this is proving to us is that that lone pair can delocalize across the entire molecule. So the whole thing is bearing the weight of that negative charge. Looking at the second one, we just have one resonance contributor here. This can pop over here to the next bond, kick this double bond off onto the end. So we have a negative charge here and a lone pair, double bond here. Also, it is good practice to put these double-sided arrows between resonance contributors, just to show that they're sort of rapidly interconverting and that a hybrid is going to exist of those two. At the end, do we have any resonance contributors at all? No. What does that mean about this lone pair, that negative charge? It is localized entirely on that carbon. It is stuck there. How stable do you think that is?
Not stable.
Not very stable at all. So is it going to want to grab a proton to fix that negative charge? A lot. Yeah, it's going to want to grab a proton a lot. So this is a very unstable base. And another way of saying that it's an unstable base is saying that it's a strong base. It really wants to grab that proton. So this is our most basic molecule because it is the least stable. Our first one was our most stable. That negative charge was delocalized across the entire thing, so more atoms are sharing the load. And it wants to grab a proton significantly less, because it has some help. That carbon in the middle has two helpers. But that is number 3. Carbon in the middle has just one helper, but that's still better than nothing. Oops, sorry about that. This should be a 1 and a 2. Any questions on that?
What would be the relationship between stability and acids?
Stability and acids. It depends on stability of what. So anytime you get an acid-base question, I would draw the conjugate base, or draw the base. The base is particularly useful because it's usually the charged species in this case. When the acid donates a proton, it's going to be H+. So usually the thing that's left behind, the base, is going to be negatively charged. Those charged species, it's a lot better to compare the relative stability of those charged species. So the relationship between stability and acidity, what I would do, draw the conjugate base, and find the more stable conjugate base. The most stable conjugate base is the one that's most likely, is the acid that's most likely to give up that proton and go to that stable conjugate base. We can do an acid-base problem later that might illustrate that a little better. Here's an acid-base problem. Look at that, fancy. Okay, what did we say about acid-base problems? What's an acid do? What's its job? It's going to donate a proton. Yeah, and a base is going to accept a proton. So, in an acid-base reaction, the only thing that's going to move is a proton. What did I say about the charge and bases? Which thing is negatively charged? The base. Yep. Negatively charged thing is going to be the base, because that can grab an H plus and become neutral. So the negatively charged thing is the base. So this is going to be our base, which means it is going to what? Accept a proton or donate a proton? Accept. Yep. So that negatively charged base is going to accept a proton. Which means that this here has to be our acid. That's going to donate a proton or donate an H plus. So if we know this H2O is going to donate an H plus, what's going to be left behind? OH minus. Yeah. So we took away an H plus. If we take away an H plus, we leave electrons behind. We have one O and one H left. So OH minus. We'll put that over here. OH minus. I'll add the sodium in later. For this, CH3, what's it called? Anyway, it's going to be the base, and it's going to pick up a proton. And that negatively charged part is what's going to grab the proton. So what's going to be at the very end of that molecule after it's grabbed a proton? SH. And what's the charge going to be? Neutral. It was negative, it picked up a positive thing, resolved the charge, it's neutral now. So let's go ahead and draw that as well. CH3, C with the carbonyl, that's called carbonyl, but that's for later. SH. Let's resolve that negative charge. Where did this sodium go?
Spectator.
It's a spectator ion, and it's positively charged, so it's going to associate with the hydroxide. You've probably seen sodium hydroxide a lot of times by now. NaOH, good old NaOH. So, we have the products from our acid-base reaction, but we look at the problem, we have one more box left, we see indicate the direction of the equilibrium by placing an arrow in the box. So what you're going to do, you're going to put an arrow pointing to the left or to the right, indicating where the equilibrium is going to lie, or I guess backwards for y'all, but left or right. What you should do, look at the most unstable thing on either side. What's that going to be? On the left, what's our most unstable thing? The charged species, the first one. That charge means it's not all that stable. It could be happier than it is. On the right, what's our most unstable thing? OH minus. Yep, that's our most unstable thing. What you're going to do now, compare the relative stabilities of those things. Negative charge versus OH. Lone pairs there, negative charge. What do we notice about the molecule on the left? What's going on there? There's something going on this molecule on the left. There's resonance. It's resonance stabilized. That's great. So, I'm going to kind of draw it out here for a second. I'll erase it. One of these lone pairs can pop in here, kick one of these pi bonds up onto the oxygen, and put the negative charge up there. So we have CH3, C. Is this bond to oxygen a single bond or a double bond now? Single bond, right. This arrow here, we broke that double bond. So now it's a single bond, lone pairs, and a negative charge. This bond is sulfur. Single or double bond?
Double bond.
Now it's a double bond. See, this arrow, we created a bond from sulfur to carbon. We added one more bond. So now, see double bond to S. How many lone pairs?
2.
2 lone pairs. Yep, we had 3, we used up 1 to make that double bond. So there's this resonance contributor. We have a negative charge on the S in the first one, negative charge on the O in the second one. Both of those are relatively electronegative species. They're more or less okay with having a negative charge, especially when it's split between sulfur and oxygen. What do we see looking now at the second one? What do we notice about that? There's no resonance at all. There's nothing to help that thing out. It is entirely localized on the oxygen. Stable or unstable?
Really unstable.
Unstable, yeah, it doesn't like that. So what is that really unstable thing gonna really wanna do?
Get a
Grab a proton. Yeah, it's really gonna wanna grab a proton and go back over to the left side. The one on the right, it doesn't care quite as much. It can kind of take it or leave it. The negative charge is delocalized across the sulfur and the oxygen. So it's got quite a bit of help. So it's going to be pushing this way a lot more than it's going to be pushing this way, the reaction. This OH is going to fight really hard to get back to the left, whereas the stuff on the left isn't going to be fighting that hard to get to the right. So where does the equilibrium for this lie?
left.
To the left. Yep. To sum that up, that was because this is much less stable than this.
So it lies to the more stable.
Yep, it wants to grab a proton to gain stability, to become water. If you were totally lost and had no idea what to do, one other thing you could notice, what do we know about NaOH, just generally speaking?
Really strong base.
Really strong base. We know it's a super strong base. Just kind of a given. If you took Gen Chem or high school chem, you know that it's a strong base. So it's going to fight really hard to extract the proton. So not even looking at all that resonance, you know this is going to fight really hard to get back to the left side. So that's another way you could kind of look at it if you were totally lost. Use all the clues you can. The first way is the definite, like the more correct way to solve it, but the second way, if you don't know the first way, definitely would help you save some points, for sure. Use everything you can if you're completely stuck. Don't just sit there. Skip it if you have to. So. Cool. If you have any questions about all that, raise your hand, and they will come help you out. I'm going to erase this, and I'll put it back up later for the key. Okay. For the structure given below, draw the important resonance contributors. So we know we're going to be moving some electrons around. Circle the major contributor. Draw the hybrid in the box provided. We have a lot of tasks. Let's just focus on our first task. Don't get overwhelmed, just do it piece by piece. Our very first task, draw the important resonance contributors. This negative charge, I would say, is where your eye should go to first. That's the thing that's going to move. When you have a negative charge in resonance, there's a saying that can kind of help you. When you're working with an anion, a negative ion, there's a saying that might help you out. Lone pair to bond, bond to lone pair. That only applies to anions. Cation resonance looks completely different. We could get to an example of it maybe later. But we have our lone pair to bond, bond to lone pair. That's going to help us out a lot. So let's make sure we have that memorized. What was it?
Lone pair to
Lone pair to bond, bond to lone pair. Lone pair to bond, bond to lone pair. Just keep saying it over and over. We have a lone pair. What's that going to do? Lone pair to what? Bond. Yeah. And there's 2 different places this can go. We'll mark them A and B. Start there. One thing that could happen could form a double bond with the carbon next to it and kick off double bond onto the oxygen. We'll call that letter A, route A. Another option we could do, this lone pair could come out here and kick that double bond up onto there. Call that route B. Which one would you like to do first, A or B?
Okay.
Let's do A, sounds good. We're gonna go ahead and draw our carbon skeleton again. Nothing changed about this nitrogen up here. This double bond didn't change because that's route B. So, in route A, we had that lone pair. And what did that lone pair turn into?
A bond.
A bond. It turned into a bond. Lone pair to bond. There was a double bond on this oxygen. What did that bond turn into?
Lone
A
pair.
lone pair. So it popped up as a lone pair onto the oxygen. Negative charge there. Be sure to show your negative charge. Just showing the lone pairs isn't enough. You have to show that formal negative charge, for sure. Are we done with route A? Is that as far as we can go?
No. We can go further.
It is all for route A.
Really?
The electrons went all the way to the end on that oxygen, and so to get back, they would have to come back here, and this bond would pop out onto here. That's just our first structure. That's going back to the first structure we had. So we don't even need to do that. So let's go to route B. Double bond up to the H. Double bond to the oxygen. Let's look back at our lone pair, the first one. The lone pair became a what? A bond, yep. Lone pair to bond. This bond right here became a what? A lone pair, bond to lone pair. And that's gonna pop up onto here. Are we done with this one?
No.
No, there is more that this can do. That was terrible. Okay. There we go. Cool. So, like we said, lone pair to bond, bond to lone pair to bond to lone pair. Lone pair is going to kick up onto the nitrogen. So see, we created a bond right here. So we're going to put that in there. Lone pair to bond. Is this bond to nitrogen a single bond or a double bond?
Single.
Single bond. One of those bonds became a lone pair, like our saying. NH. Two lone pairs on the nitrogen. What's the charge on that nitrogen? Negative. Notice how in all of our resonance contributors there is a negative charge. Make sure that stays there. You have to conserve that charge. It's not going anywhere. Is that all we have?
Yes. Yeah.
Yes, that is all of our resonance contributors. But look back at our problem. Draw the important resonance contributors. That's just step one. Next, circle the major contributor. The very first thing, when you're looking at major contributor, decide if every single atom has a full octet in every single resonance structure. Take 20 seconds to do that. You can talk to people. Decide whether every resonance structure, every atom has a full octet or not. See if you can find anywhere that's missing a full octet. There may not be one, just be sure for yourself. In this case, every resonance structure has a full octet. Every atom in every resonance structure has a full octet. That's the very first thing you do though, because if any of the resonance structures is missing a full octet, you know that's not going to be the major contributor. That's the very first factor you need to consider. So if any of your resonance contributors give you full octets on everything where there weren't full octets before, that's your major contributor no matter what. So we know all of these have full octets on every single atom. So now what we have to look at are where these charges are located. On what atoms are they located? And where are they happiest? In all of these resonance contributors, we have the negative charge on carbon, we have it on nitrogen, and we have it on oxygen. Where is the negative charge going to be the happiest?
Oxygen.
On oxygen. Yep. Do we have any resonance contributor where the negative charge is on oxygen?
Yes.
Yes. That is our major contributor right here. Negative charge on that oxygen. We resorted to that only because every single one had a full octet. That's the very first thing you do. check octet rule. After that, go to electronegativities. So, we circled the major contributor. Now, draw the hybrid in the box provided. What I would do when you have to do that is draw the skeleton first, but no pi bonds. So single bond up to the oxygen, single bond up to the nitrogen, with a hydrogen up there. It's okay if it goes out of the box a little bit. She's not going to be mad. Hopefully. So, next thing I would do, every single place that there is a negative charge in every single one of your resonance structures is going to carry a partial negative charge. Because remember, only the hybrid exists, and so you're delocalizing that negative charge over several different atoms. So what you're going to do is look through your resonance contributors and see every single atom that has a full formal negative charge. In your hybrid, it's going to carry a partial negative charge. So let's look at our very first resonance contributor right here. Where's that negative charge? The bottom carbon in the cyclohexane ring. So right there, we're going to have a partial negative charge. Going down route A, where's the negative charge now? Oxygen. We're going to put a partial negative charge on that oxygen. Just going to go ahead and finish that for you, and then up onto the nitrogen. So there are 4 partial negative charges. We also see that all along the way, through our resonance contributors, every single one of those places is a part of a double bond at some point. What that means for the hybrid is that it's going to have partial double bond character throughout that entire system. So you're going to start down, so this oxygen right here has a double bond. You're going to start from there and put a dashed line, that doesn't look very dashed. You're going to put a dashed line everywhere that there's a double bond in any resonance contributor. Yes? Scroll down. Am I you good? Cool. No, you're good. So put a dashed line everywhere there's a double bond in any resonance contributor. So we already did the first bond. How about the next one? Is there a double bond in any resonance contributor? Mm-hmm. Yes. There is a double bond there in this one, right there. We're going to continue throughout the whole system like this. I'll just give it away every single time there is a double bond.
Is that a dashed line?
It's a dashed line, yes.
Okay.
And what that means is that there is a partial double bond character. Those double bonds are changing location rapidly, but only the hybrid exists, so there's going to be partial double bond character throughout that entire system. And that dashed line tells you that it's not a full double bond, it's just kind of partially a double bond. So that is what your final hybrid will look like, with your partial negative charges on those atoms.
So, does the major one not have to, do we not have to show that the major one contributes more than the minor ones?
I would say in this case, no. It's a little difficult to show that graphically.
Yeah.
As long as you have the partial negative charges on the correct atoms, and as long as you show partial double bond character where there is partial double bond character, you're fine.
So for the partial charges that you show, all of them, not just the one that we chose as the one with the largest quantity.
Correct, yes. So his question was, should we show, or we should show all of them, all of the partial charges, not just the one we chose as the major contributor. Yes, that is correct. Everywhere there is a negative charge throughout all of our resonance contributors is going to be bearing a partial negative charge. Raise your hands if you have any questions on that one. Stick up for yourself. Resonance is tough, for sure. It's a concept that's difficult starting on Norgo, so don't be afraid to get some help, for sure. All right, so we're going to move on. This is also a tough concept for a lot of people. I kind of wanted to go and talk about a little bit of other stuff for a hot second. So with hybridization, the first thing you need to know is that total there are 1 s orbital and 3 p orbitals. So you have 1 s and 3 p's unhybridized. The other thing you need to know is that pi bonds are made of unhybridized p orbitals. That'll make a little more sense in the context of an example. So look at that, we have one. This is the cyanide ion. And let's look at this carbon and determine its hybridization. First, we have to count the number of pi bonds on that carbon. How many pi bonds are on that carbon? 2 pi bonds, yep. One here and one here. One of these is a sigma bond. We are not going to count that sigma bond. So we see that there are 2 pi bonds on this thing. So how many p orbitals do we need to make those 2 pi bonds? 2 p orbitals. We're going to need 2 p orbitals. We're going to have to save 2 of them separately. So let's draw this out again. We have an s and 3 p's. We know we need to save 2. What's left? sp. Those will hybridize. So this is sp hybridized. Hopefully that helps clear up a little bit on finding the hybridization of an atom. If you have any questions about that, raise your hands now, because it's going to get harder. This problem, we're going to go back up and do some more. Okay, let's do it. Okay, consider the structure below and answer the following questions. First one, write the hybridization of each atom indicated by an arrow in the box provided. So we see on our molecule, there's a bunch of different arrows going on here. What's one thing we may need to consider?
Resonance.
Resonance, yes. And we'll talk about why in a hot second. But let's go ahead and draw the other resonance contributor. On here, there's a lone pair on this nitrogen. That can come into that bond, form a double bond, and kick this pi bond out onto the oxygen. What that would then look like, oh no.
It's gone.
She gone. I don't know where we went.
Who popped it? Oh, there it's back.
Oh, cool. Okay. This didn't change, so I'm just going to go ahead and draw the rest of this. C,
Not like
triple bond to C. CH2. Boy, I'm running out of room. I'm sorry, guys, I'm going to have to redraw this. CH. C. Okay, that's triple bond to C. CH2. Now we're getting into the stuff that changes. So this bond to oxygen, is it now a single bond or a double bond? It's now a single bond. You can see in this first arrow here that one of those bonds kicked up onto the oxygen. How many lone pairs were there before? 1. How many are there now? 2. So make sure we get all of that right. So single bond to the oxygen and 2 lone pairs on that bad boy. What's the charge? Neutral. It was positively charged and it picked up some electrons. So now it's neutrally charged. We're going to keep going. Is this bond to nitrogen a single bond or a double bond? It's now a double bond because we see this lone pair right here came and formed a double bond. We have that double bond now. HCH3. Does that look good? There's something missing. What is it? Positive charge on the nitrogen. Remember how we were going to conserve our charges in all of our resonance structures? That positive charge that was on the oxygen has to go somewhere. And that nitrogen, it had that lone pair all to itself. Now it has to share it. So it lost ownership of 1 electron. So now it's short 1 electron. So it's a positive charge. So we have that positive charge there. We'll talk about why that resonance why these resonance contributors matter in a hot second. Let's look first at this carbon C. That doesn't change in either of our resonance contributors, so we don't need to worry. Let's look right at it. How many pi bonds do we have on this carbon right there? 2 pi bonds. So how many p orbitals do we need?
2.
2. So if we had 3 and we take out 2, how many do we have?
One.
So it's sp hybridized. 2 of the p's went away. So this is sp hybridized.
Oh,
The other 2 p's are right here. They're in that double and triple bond, both of those pi bonds. Let's go to the next one. It's pointing to the oxygen. Notice in our resonance contributors, one of the oxygens has a double bond, a pi bond. One of them doesn't. What do we know about resonance contributors? Only the hybrid exists. So it's going to be a hybrid. What that means is that this oxygen here is going to need to leave a p orbital free for this pi bond. So when you're looking at these, and you have resonance contributors that have differing number of pi bonds, go with the one that has the highest number of pi bonds for just the atom you're looking at. So in this case, for the oxygen, we're going to go with the first resonance contributor, because it has the highest number of pi bonds, and we know we're going to need to keep those orbitals free to make those pi bonds. So let's look back at that. How many pi bonds do we have? One. We have 1 pi bond, so how many p's do we need to make that? 1. We need 1 p. If we have an s and 3 p's, we take 1 p out. How many do we have left?
SP2.
2. So what is it hybridized?
SP2.
sp2. Yes. Great. Moving right along. So now we get to this nitrogen. How many pi bonds are in this structure? 0. Let's look at the other structure. How many pi bonds on that one? 1. We're going to go with this structure for that atom, because we know it needs, at some point, to keep that p orbital free. So we're going to use that structure to count our pi bonds. How many pi bonds are there? 1. How many p orbitals do we need to make that pi bond? 1. So what is that hybridized?
SP2.
sp2, because we took one of those p's away to make the pi bond. sp2. Great. Okay, so that's part A. Full points, we're good. Part B, what is the carbon C, carbon D, carbon E bond angle? That's tough if A, you don't know what the orbitals look like, or B, you haven't memorized the geometry. You have to have done at least one of those things though. That's the catch. There's no way around it. There's no secret trick for you. So we look carbon C, carbon D, and carbon E. We're going to look at carbon D, the hinge point, and we're going to see how that carbon is hybridized. So let's find carbon D in our structure. It's right here. Carbon D. How is carbon D hybridized? sp3. Yeah. How many pi bonds are there? 0. No pi bonds. So we don't need to take any p orbitals away. All 3 p's can hybridize. sp3. So it's sp3 hybridized. What shape does an sp3 hybrid make?
Tetrahedron.
A tetrahedron. What is the bond angle for a tetrahedron? 109.5. There's no way around memorization on that one. You have to just know that. Sorry to be the bearer of bad news, but that's the way it is. 109.5 degrees. That's your bond angle. All right, letter C. The sigma bond between carbon A and carbon B is formed by the overlap of what types of orbitals? Be specific. When she says be specific, what she wants you to say is how they're hybridized, sp, sp2, sp3, something like that. So we're going to look at carbon A and carbon B. Let's find those. Carbon A, carbon B. Carbon A here. How many pi bonds are on carbon A? 1. So how is it hybridized?
SP2.
sp2. So this is sp2. Those sp2 hybrids are going to make up all of the sigma bonds. So when it's asking, the sigma bond between carbon A and carbon B is formed, and it's formed by the overlap of some orbitals. We know that carbon A is sp2 hybridized, so the first one is going to be an sp2 hybrid. Carbon B, how is that hybridized?
SP.
sp, just like its neighbor. So you would say that that bond is formed by the overlap of an sp2 hybrid and an sp hybrid. That's as specific as you can get.
Can you put, if when you're writing it and you put it in like SP2 hyphen SP, is that fine? They won't take points off of that, right?
He was asking whether you could put a hyphen between them. I'm not sure exactly how she wants it formatted. I imagine they would be a little bit flexible if they knew you knew the answer. So I'd say if you put SP2 and then dash SP, just to show that there's a bond or something like that, I'm sure that would be fine as well. I'm not exactly sure on the formatting, so you would have to ask Dr. Bean or Dr. B on it, respectively. That's not really a question for me, unfortunately.
Okay.
Worst case scenario, I know for sure this would be accepted. You can say and or a plus sign. So it's formed by the overlap of an SP2 and an SP. You can use a word if you want. So and plus sign, I think that's all fine. Cool. That's our hybridization cheat sheet. I'm going to skip that. All right, number 10. Arrange the Newman projections below in order of increasing strain energy. So more strain is going to be our 3, and the least strain is going to be our 2. So there's something interesting going on with number 2. 1 and 3 are in what are called a staggered conformation. Number 2 is in what's called an eclipsed conformation. Eclipsed means that this group in front and this group in back are going to be much closer together than they could be. They're going to line up. Good or bad?
Bad.
Bad. Yeah, you don't want that. Strain energy. There's going to be some strain there if you put 2 big groups right next to each other. Additionally, if you look at the groups on the front carbon, actually I maybe should have led with this, but how Newman projections are organized, this center dot here is the front carbon, and the ring back here is the back carbon. And we're looking along the bond from that front dot to the back. So you're not going to see it, because the front carbon covers it up. But there's a bond there between this dot and this ring. This dot and this ring. There's a bond there. We're looking at all the other stuff connected. This middle one, eclipse conformation. Additionally, we can look at the front carbon and we see the bulkiest group is this isopropyl right here. That's the biggest thing. On the back, the bulkiest group is this ethyl. We have to compare ethyl versus methyl versus hydrogen. So ethyl wins. So not only is this in an eclipse conformation, you have the biggest group on the front next to the biggest group on the back. Good or bad? That's the worst possible one. So how much strain energy is that going to have?
The most.
A lot. There's a lot of strain. So that is going to be number 3. That's going to win automatically. These other 2 are in a staggered conformation. That's a lot better. But you can still compare the 2. So you look at the carbon on the front. What's the bulkiest group on the front? We said before, it was this isopropyl. We want that to be as far away as possible from the bulky groups on the back. The bulkiest group on the back is this ethyl again. Noticing anything?
Closer.
On the first one, they're right next to each other. It's not eclipsed, but they're still close together. There's a better way to do it. On the third one, they're as far away from each other as they can possibly get. Full 180, and they've got that bond separated. So that's the best we're going to get. So is that going to be the highest or lowest strain energy? Lowest, yeah. Littlest strain possible. Order of elimination, that's 2. Any questions on that? Raise your hand, get some help. We'll draw a Newman projection later too. I'm gonna do it on time. 8:20. Cool, good. Okay. Draw the more stable chair conformation for each of the substituted cyclohexanes shown below. When you're doing chair conformations, there may be bulky groups, bulky substituents on the chair. And there are 2 places that they can possibly go. They can be in the axial position or they can be in the equatorial position. What that means, say here's your ring. Axial would be on an axis, straight up and down. Equatorial, it's going to be sticking out to the side, out like that. You want the bulky groups to be out and away, equatorial. You don't want them to be axial, because then they're close to all the stuff. They're close to the ring, close to the hydrogens there. If there are any other substituents, they're closer there, and that's more strain. Like we saw with the Newman projections, we want those bulky groups to be far away. So you want to put those in the equatorial positions. So what I would do, let's look at A first. I would find the bulkiest substituent. Which one is the bulkiest? The top one, that T-butyl group. That right there is our bulkiest group. So do we want that in the axial position or the equatorial position?
Equatorial.
Equatorial. Yep. We're going to decide that this is equatorial. What I'm going to do now, I'm going to draw our chair. Quick way to do that, draw two lines, one of them a little further than the other, like that. Draw a triangle, connect that. Draw a triangle, connect that. You can do that likewise on the other one. One a little further than the other, connect that, connect that. There's some chairs. I'm not the best artist, so I'm sure y'all can do better, but that's my quick way of doing it. So, we want that T-butyl group to be in the equatorial position. Do we need it to be up or down?
Up.
Up. That's given to us in the problem. We can't decide to put it up or down. That's given to us by this wedge. That wedge there means that it is up out of the plane. These dashes mean that that group is down out of the plane. And we can't decide. That's the way the problem is given to us. So we know that that T-butyl group has to be up and equatorial. So could we put it there? No. Yeah. That one has to be up axial. Remember too that each of your carbons has to look like a tetrahedron. Needs to look like an sp3. They're all sp3s, so they're all going to look like tetrahedrons. So it has to look like that with those three tripod legs coming down and one coming straight up at the top. It can also look like this with the tripod legs coming up. So in this case, you have one here, one here, one here. Legs of a tripod coming up, and then straight down. Every single one of those has to look like that. You actually will get points off if they don't look like tetrahedrons. I got points off on my first exam for that. I was really bitter. I was sad. So that's very important. So if we know that has to look like a tetrahedron, we know we can't put our T-butyl group here, because what did we say we were going to do with that? We're going to put it in the equatorial position. So what do? We're going to move it to another carbon. We're not going to put it on that carbon. Over here, remember we saw that those tripod legs were going up. This here, is that up and equatorial?
Yes.
Yes, it is. Which is great. So we can put our T-butyl group there. What is also attached to that carbon? Hydrogen. I would go ahead and show all of the hydrogens that are also connected to carbons with substituents. You don't necessarily need to show hydrogens all the way around the ring, but I would definitely put them anywhere you have a substituent. This hydrogen here, is it pointing up or down? Down. Is it axial or equatorial? Axial. Notice, on every carbon, there's going to be a pair. And the up, down, axial, equatorial have to flip. You can't have something on the same carbon being up axial and up equatorial. Likewise, you also can't have it be down axial and up axial. They both have to flip. So on this pair, we have an up equatorial. So what has to be on the downside? Down axial. It always flips both ways. So now we have to decide these other groups here. We already picked the biggest one, and we know that they alternate. So we have to follow a pattern. If we put this group here in the equatorial position, and we go one carbon over, This has to be up, so what does it have to be? Axial or equatorial?
Axial.
Axial. It has to alternate. The next carbon over has to be up axial. The other thing, make sure you're going around the ring the same direction. So this is clockwise from our T-butyl group. So we're going to have to put that CH3 clockwise from our T-butyl group, which is going to be right here. CH3. And a hydrogen attached to that as well. Now we're going to go counterclockwise. We're going to go counterclockwise over 2 carbons. So let's go from a T-butyl group. We're going to go counterclockwise 2 carbons. 1 carbon, 2 carbons. There it is. We know that that's down. One good way to figure it out is go around the ring and stay on the same side of the ring. So see how this first T-butyl group is up equatorial? The next carbon over was up axial. So what's this one?
Equatorial.
Equatorial. It has to alternate, remember? This one is up what? Axial. So this one is what? Up what? Up equatorial. It alternates all the way around the ring like that. So if we know that on that carbon we have an up equatorial group, or possibly hydrogen, if that one's up equatorial, what does the down have to be? Axial. So this is down axial. Erase that, just to make it clear. If you don't understand how we arrived at all of these up equatorial, down equatorial, how we arrived at all those answers, raise your hand and get some help. I would say this is like 100% going to show up on your exam. For sure. So get up. For sure. Cool. We haven't finished this one yet. We found that 4th carbon. We decided now it's down axial. So down, we're going to point that straight down. Oops. And our CH3 was down. So CH3 and H. So we are done with that one. Let's go ahead and run the next one. Okay. First thing we do, what do we do first?
Biggest group.
Yes. What do you think? What's the very first thing we do?
The equatorial. Biggest group on equatorial.
Biggest group on equatorial. I heard it a couple times. You want to put the bulkiest group in the equatorial position. This T-butyl group is by far the bulkiest group. We have CH3s. So, oops. Sorry guys, that's an H. What we're going to do, we're going to put this T-butyl group in the equatorial position. And it's up equatorial. So if this here is also up, and it's 1 carbon over, is it axial or equatorial?
Axial.
Axial. So this is up axial. Let's keep going around the ring. What's this one?
Up equatorial.
Up equatorial. How about this one? Up axial. And how about this one? Up equatorial. Conveniently, these are all 3 on the same side. So we don't have to do that thing that we did last time where we went on the up side the whole way around and then switched it to down because it was down. All of these are up, so we can just follow our pattern. We're going to erase the ones that we don't care about. Cool. So we have our chair conformation here. And we know we want that T-butyl group to be up equatorial. So is this a good place to start, that carbon? No, we can't put our T-butyl group there. Because if we put it here, we would either have to break the axial equatorial or the up down. Because if we put it on the upside, it would be up axial. If we put it on the downside, it would be down equatorial, but we need it to be up. Problem gave it to us as up. Even though it's nice to have it in the equatorial position, this wedge tells us that it has to be up. So we need to find another carbon.
Bottom right.
Let's go right here. Yep. So we have our 3 legs of a tripod right here, then straight down. We want that T-butyl group to be in the up equatorial position. This up right here is equatorial. It points away from the ring. So we can put that T-butyl group right there. On the bottom side, there will be a hydrogen. Let's first go clockwise to that first CH3 right next to it. See, it's clockwise here. So likewise, we're going to have to go clockwise on our chair. So clockwise, 1 over. We said this was up axial. Conveniently, we already drew it. We know that there is an axial bond in the up position, or an up bond in the axial position. Either way, actually. So we've got our CH3 up axial. What else is connected to this carbon right there?
Hydrogen.
Hydrogen. Yep, so we can go ahead and show that as well. Let's keep going clockwise. So from that CH3, we just added 1, 2, 3 more carbons over. So from here, 1, 2, 3 more carbons over. We're going to be right there. And we said this was up equatorial, which is great. That fits our 3 legs of a tripod and a straight down model. So the CH3 is up and equatorial. This right here is an equatorial bond. So we're going to put our CH3 right there. And nitrogen. You don't, again, need to draw all of these hydrogens. It's really messy. She doesn't put them on her keys, so I think it's fine. Okay, so we have 2 chair conformations. Now, part B. Which isomer is more stable, A or B? We were talking about stability with equatorial and axial. Where do we want our groups to be?
Equatorial.
Ideally. Equatorial. Especially the bulkiest group. The bulkiest group has to go equatorial. But let's look at these. Actually, let's even look at the top. Let's not even look at our chairs. We see that one of these groups is, our bulkiest, is equatorial. We see that our other 2 groups are both axial. Right? So we have 1 equatorial group and 1 axial group on that chair. On this chair here, we have 1 group equatorial, we have 1 group axial, and then another group equatorial. So we have 2 equatorial and 1 axial. Which one's better? Did we want equatorial or did we want axial?
Equatorial.
We want equatorial. So we're going to go with the chair conformation that puts more groups in the equatorial position. Don't confuse that with how you start the problem. You always start putting the bulkiest group in the equatorial position, no matter how many other groups end up equatorial. You want that big, bulky T-butyl group to be out and away. When you're looking at which one is more stable overall, then you take into account the total number. So in the left one, we have 1 equatorial, 2 axial. On the right one, we have 2 equatorial, 1 axial. So this B right here is going to win. If you have any questions about that, raise your hand. I would say something almost identical to this problem is probably going to show up. So get help if you're confused. What's that?
What if for B you put the T-butyl on the bottom right and went that way? Would that have been the same? Because it's still equatorial upwards.
Yeah, that's a good question. So he was asking about if there were other places you could put the T-butyl group. The answer is yes. These 2 chairs are not the only right answer. These aren't the exclusive correct answers. Because, so say, let's look at A, and let's look at the T-butyl group. I put the T-butyl group, I'm going to switch colors here, make it a little easier. I put that T-butyl group right here. There's another spot that you could start drawing this ring that gives you an up equatorial bond. Right there. So you can put it there. Likewise, you could have also started it here and put the T-butyl group there. All of those answers are fair game. What you want to do is make sure that axial and equatorial are correct and that up and down are correct. There's multiple places you can start from. Make sure you go around the ring the same direction, so don't reverse your directions. If you're gonna draw it like going clockwise, make sure you continue to go clockwise when you're drawing your chair. Other than that, there are a few other answers that are fair game. So my answer isn't exclusively the only answer. Do you have a question, Sil? Cool. Awesome, that's a great question. So my answer isn't the only correct answer. You would get points for any of them. As long as up and down, axial, equatorial are correct, and that you go the same direction around the rim. You're safe. What's up?
Do we have that number on carbons?
No, you don't. You can though. I don't do it. You're more than welcome to. Numbering though, it doesn't matter where you start numbering in this case. The numbers are only really specific and critical when you're naming. You can number these carbons if it's a helpful tool for you. What that would look like would be, maybe you would start numbering from the TBO group 1, 2, 3, 4, 5, going clockwise around the ring. You can pick any number you like. Then what you would do, you would find where you started your TBO group on your chair confirmation. 1, 2, 3, 4, and 5. That's perfectly fair game. You can number it any way you like. It might be a helpful tool for you. I don't feel like I need to. But that's up to you. If that helps you, totally fair game. Cool. Let's go ahead and move on just for the sake of time. We are going to skip this for now and come back. I know a lot of you are anxious to go over this, but Dr. Leonic's class does not cover propagation of free radical halogenation for this exam. So we're going to skip it just for the sake of time, and if you would like to go over it, we definitely will. It might be in a little bit though. We're going to skip for now.
So we're going to his exam now?
So now we're moving over to Dr. Leonic's exam. This is his 2018 exam. I'm skipping all of the problems on the first page because every concept in there is covered on Dr. Bean's exam. We've already done all of that. Problem number 2, nomenclature, also covered on Dr. Bean's exam. Same principles apply here. What would be good to do would be to do those problems and check his keys. They're all online. You have access to those. So go ahead and try them and see if you get them right. Make sure you can get them right. That would be a helpful thing to do. We're also going to skip this one for now because Dr. Bean's class doesn't cover it. So we'll do that at the end as well. Okay, this is a great question to cover for every class. Actually, it helps for every class just understanding this. So, it's kind of a tough question at first. Don't get overwhelmed. Put pen to paper and start drawing. Let's read it. The following compound can become protonated on any of the 3 nitrogen atoms. I went ahead and labeled them A, B, C. It can become protonated. One of those nitrogens is much more basic than the others, however. Draw the important resonance structures of the products of protonation on each of the 3 nitrogen atoms. Then determine which nitrogen is the most basic. That's a lot. That's a lot to absorb all at once. Let's dissect this problem a little bit. Following compound can become protonated. What does that mean the compound is if it's accepting a proton? Base. It's a base. One of those nitrogens, A, B, or C, is more basic than the others. In other words, it is more willing to accept that proton than the others. Draw the important resonance structures of the products of protonation on each of the 3 nitrogen atoms, and then determine which nitrogen is the most basic. I did a little bit of this work just for the sake of time. So what I did, I went ahead and added a proton on each of the 3 nitrogens, A, B, and C. And I went ahead and circled here, A, B, C, for where I added protons on each of those nitrogens. Notice, there's no charge at the beginning, and we're adding a proton, adding an H+. So what's going to be the charge on all these? Positive. Okay, you have a question?
Yes.
What's up?
Sorry, what
Okay.
exam is that?
This is exam 2018, fall of 2018 for Dr. Leonic. Oh, so if you Google ACS UH, we actually have it posted for you. So it is 2018 exams, so Google ACS UH, and it'll be under practice exams.
Why are you doing this to me?
So, what I would very first do is draw all 3 of those protonations. which is all it's asking you really to do. And then we evaluate each one. We'll see if there are any resonance contributors that help stabilize, anything like that. Let's look at letter A. Is there any resonance that can happen here?
Not on the first one.
You might think right at first glance that double bond there can come over there and fill that plus charge.
But with the hydrogen.
But can nitrogen have more than 4 bonds?
No.
No. It has 2 bonds to carbon already and 2 bonds to hydrogen already. So can it accept any more?
No.
No. So is that positive charge stuck there?
Yes.
Yep. There's nothing we can do. It is entirely localized on that nitrogen right there. So no resonance. Moving on to B. Likewise, we might say that this comes over here to bond with that nitrogen. Can that happen? No, can't accept more than 4 bonds. So likewise, there is no resonance here. Let's look at letter C. Positive charge, what does that mean? Is it missing electrons or does it have extra electrons? It's missing some electrons. So what might we do to put some extra electrons here? This double bond can actually come out here as a lone pair.
Is this resonance?
Is this carbon to nitrogen bond a single bond or a double bond now? Single bond. Yep, we turned it from a double to a single. So that lone pair went out onto the nitrogen, H2N. What's the charge on that nitrogen now?
Neutral.
Neutral. It was positive, picked up 1 electron, because it had half of the ownership of that bond, but now it has full ownership, so it picked up ownership of an electron, so now it's neutral. Where did the charge go? Because remember, our charge is conserved,
To the
right? So where did that charge go?
carbon.
The carbon. Yeah. So a positive charge means it's missing electrons. The thing that lost electrons here is this carbon. There was a bond that is no longer there, and nothing came to replace it. So that positive charge is now on this carbon. And then nothing changed here with this NH2. So already, before anything even happens, we already know that C is resonance stabilized. Just to be sure. Okay. So already we know there's resonance stabilizing this thing. So it's more stable than the others when it accepts a proton. So already, which one is the most basic? Which one is the most likely to accept a proton? Nitrogen A, B, or C? C. C is the most stable once it's accepted a proton. So once it's grabbed that proton, it's the most stable compared to the others. There's resonance stabilizing that. So it is the most likely to pick up a proton, which means it is the most basic. We can go a little further. There's actually more here. The nitrogen up here, right here, is there anything hiding there?
A lone pair.
A lone pair. Yeah, they may not give those to you.
So that would be.
That lone pair can come down to fill the void. So we have another resonance contributor. And H, is this nitrogen to carbon bond a single bond or a double bond?
Double.
It's now a double bond. Yep. Single bond, H2N, NH2. Where did our positive charge go?
Nitrogen.
Onto the nitrogen, the one that donated a lone pair. So it lost ownership of an electron. So it's missing an electron now, positive charge. Sorry for all those notifications, guys. Likewise, there's another lone pair right here. Same process can occur. Actually, let me go ahead and draw this in a separate color. This other lone pair can come and do a similar job. Where's the double bond?
The bottom right.
Bottom right, right here. Yep, because remember this lone pair right up here came and formed that double bond. Where did the positive charge go?
That nitrogen.
That nitrogen, yep, because that's the one that lost ownership of an electron when it donated its lone pair. So it lost ownership of an electron, positive charge is there. Again, notice the charge is conserved. In all of my resonance structures, the positive charge is somewhere. That's a good way to check yourself, to check if your resonance structure is right. Because if there's no positive charge anywhere and you're sure of that, it's probably not a correct resonance structure. So make sure to preserve that positive charge throughout. So looking at this overall, so draw the important resonance structures of the products of coordination in each of the 3 nitrogen atoms, then determine which nitrogen is the most basic. Your answer would be, because of this resonance, there is delocalization of the positive charge. I wrote that really big. So, therefore, more stable conjugate acid. If you have a more stable conjugate acid, what is a conjugate acid? Did that just throw you all for a loop?
No.
Talk to your neighbor for 5 seconds, just make sure you know what a conjugate acid is. Ready, set, go. Make sure you know, if you don't. Because there's no point in me doing this if you don't know what a conjugate acid is. Are y'all good? Does anyone have any questions about what a conjugate acid is? Okay, so if you have a more stable conjugate acid, that base is more likely to accept the proton to go to that conjugate acid. So that would be a great answer. Full points, no problem. Okay, here's a good one. This is a great one for Dr. Bean's students as well. So drawing Newman projections. You may be asked to do this. This is a tricky problem too, because it asks you to draw a Newman projection of that. They don't even show you the shape. So let's read this whole problem. Draw Newman projections along the C3-C4 bond to show the most stable and least stable conformations of that guy. I'm not even saying. Very first thing I would do, draw it. We know it is a heptane, which is how many carbons? 7. So I draw 1, 2, 3, 4, 5, 6, 7. Now we look at our substituents. We can number it however we want since we're drawing it. On 3, we have an ethyl, which is how many carbons long? 2. 1, 2 carbons long. Or number 3. What other substituents do we have here? 3 methyl groups on 2, 4, and 4. Here it's 2. And 1 up here on carbon 2. And on carbon 4 here, 2 more methyl groups. Okay, now we've drawn this thing. Now let's go back to the original problem. Draw Newman projections along the C3-C4 bond. So C3, let's start with that here, is right here. C4 is right here. What I'm going to do, I'm going to put a little circle here. That might help us later. So we're drawing a Newman projection along the C3-C4 bond. What that means is that C3 is going